I changed the second quiz to 9 o'clock because we might do that in class. Could be after class.
But the Shobi one is due that day.
Yeah. So I have those. Okay, let's look at Shobi. Make sure everybody understands that. So we do have a lot due by next Wednesday. I would have normally liked to have the test bonus already due today, but I decided I wanted to wait until everybody finished their makeup test, so today's post is test bonus. So okay, so we have the test 3 bonus is worth up to 10% or 10 test points, 10% on your test grade. Even if you replace that test, you still get to keep it because I keep that in a separate column. So that's a test bonus. It's not due till next Wednesday, but get it done because, you know, it's test 3. I changed this quiz solving exponential and logs equations because that's over section 3.4, and that's changed to 9 o'clock. We're going to cover maybe just the first page. We're probably doing that in class, although I probably will want you to put it in there anyway. We have a Socrative. I don't know if you were here when we did that. I go into a Socrative and I have the same quiz as something you take on your computer or device, and you learn from it, and then I may have you post it anyway. So it's not due till 9 next Wednesday. Section 3.2 worksheet was supposed to be due today. I changed it to next Wednesday. Okay, so and I decided we didn't have time to make test 4 review be due. It's not going to be due. I'm going to post the solutions. It's a good idea to try to work through that, but it's not going to be a grade. So I removed the due date, so it moved it down, but it's down there. But because of time issues, I have to cover a certain amount of material, and yeah, we have a lot of material to cover, as you can tell, right? Any questions? Did I answer your question, Madison? I guess I did.
Yeah.
Okay, good. Okay, so yeah, and I try to go in here and give you reminders and stuff. If you have Shobi set up right, you'll have. But they sent me this today that there's a survey, student satisfaction survey. They're wanting you to fill out before Friday, April 13th. It's not a grade in this class, and if you've already filled it out for one class, you don't have to do it for every class, just once. Fill it out once. They're just trying to get some feedback from surveys from students about how satisfied they are. Okay, and so somebody asked what the class average was on this test. It was a 62.4%, and the median grade was 66.8%. And that's just I didn't count the internet people with that. So that's the in-class people, the people that come every Wednesday night. So, all right. Any questions? So that's what's due. We're going to probably do the quiz properties of logs today, but you still have to enter your answers by next Wednesday, but you have to show work on numbers 1, 2, 3, and 6. But you will know the right answers because we're going to go over it. Okay. So, all right. This hopefully to help you learn the material. Okay. So this is section 3.2, logarithms. And logarithms, last time we went over exponentials, logarithms are the inverse function. Logs are inverses of exponential functions. Okay, and so first we have the definition of logarithmic functions. Remember, exponentials, like y equals 2 to the x, look like this. Had a horizontal asymptote there. And when we did the horizontal line test to see if it had inverses, it does have an inverse. And its inverse is this function. Y equals log base 2 of x. That's its inverse. And what will be, and there, it has a vertical asymptote at x equals 0, and it's, if you flip it about the line y equals x. Remember, inverses from section 1.7 flip about the line y equals x. Anyway, so that's what we're covering. We're doing logs now, and we had no, so we knew this had an inverse, so they made up logarithms a long time ago to be what we're going to call those the inverses. So y equals, let me get my, I always like to have my answers out. Actually, that's up. So y equals log base b of x is equivalent to, this is double arrows in that, b to the y equals x. So we can, so this is the base, and this is the base. And this is the exponent. So on this side, the y is the exponent. So logs are exponents. Y was an exponent, and the y equals, so logs are exponents. Okay, and we can convert between logs and we can convert logs. These are equivalent. We can convert with this pattern. I was supposed to write it, I was going to write it this way. Okay, there's a pattern in pre-calculus for dummies. They use a little snail. And what was the snail in SpongeBob called? What?
Gary.
Gary. So I went to they call him Gary, and I'm still trying to get this information from him. But if you can make a snail's body out of this. But b to the y equals x. You start with the base. This is equivalent to b to the y equals x. And they have and I haven't been able to get it because I don't know my Google password. I asked for this. I went to a training, a conference, and this teacher had this, talked about Gary the snail, and this is I think that this is the snail's shell. You know, I can't draw.
It's okay.
I don't know. Is that a snail?
Snails don't have feet, but it's okay.
Oh, they don't
They
have
have one foot.
Anyway.
It's okay.
Anyway, okay. I'm thinking turtle, right?
Yeah.
Anyway, Gary the snail, in Calculus for Dummies, they use a snail, and then this person took that snail and called it Gary because of SpongeBob, you know? Anything to help people remember things, but anyway. You start with the base, you kind of make a shell shape here with these arrows. is a base to the other side of the equal sign, that's the exponent. B to the y equals x. And there's a pattern, and this is how you go back and forth between logs. So it's a snail named Gary, I guess. And I'll get that information from her. I just have to look up my password and all that. But okay, so one skill you need to be able to do is just convert from logs to exponents. And so it's easier if you put the equals 2 on this side. And then you just do this pattern. You start with the base, subscript is the base, go across the equal sign to the exponent, and then that equals what's inside the log. So it's 9 to the second power equals x. And that's how you convert between, so it is kind of a snail shell shape there. 9 squared equals x, and we're just writing it in its equivalent exponential form. If we were solving for x, then of course we would say x equals 81, but we're not solving equivalent form. What's the next one, guys?
120, wait, no. It's going to be, is that an S? No, that's a 5. That's a 5. 5 to the 120.
No, let's do, try.
Okay, so 5 to the Y. Yes. This is the base, the 13 is the base, and the 2 is the exponent.
So what I do on these is I'm going to convert it to a log. So I write L-O-G. Okay, the base goes right here. The base is 13, so I put a subscript 13 here. The exponent is across the equal sign because logs are exponents. So adding 2, now leaving space to put the x in. The x has to go in the only up space available. Now you can check with your arrows that you did it right. 13 squared equals x. Yes, we did it right. So you could, that's what I do to convert from x. So here's the is b, the exponent is 3.
Space and put equals the exponent 3.
And then we're going to put in the 343 right here. I needed to leave a little more space maybe, but. And then check to see if, do the arrow and see if you did it right. And it's that pattern. 43. Okay. And we have basic
Properties involving 1. Okay, if we have log base b of b, and we want equals, so we're going to, and we rewrite it in its as equivalent exponential form that's to the x equals b. Well, what power do you need to raise b to get b? 1. So x must be log base b. Okay. And that's what b to the 1 equals. So if you if we want to know what that equals, we can rewrite it. It's b to the x equals 1. So what power do you raise b to get 1? X must be 0. That's what this is saying. Log base b of 1 equals 0 because 0 is the x must be raised to obtain 1. Anything raised to the 0 power 1. So x must be 0. So that's what that equals. So this is true no matter what the base is. So these are the two properties involving 1 is log base b of b always equals 1 and log base 1 is equals 0. No base has to match what's inside the log. If those match, and that's what we have, then get 1. If we have the log of 1, any base, it's going to be 0. Okay, so we can evaluate some simple logarithms without our calculator then. If we want to evaluate log of 9 base 9, notice that these match. So we get 1. And what's a log of 1 base 8? The log of 1 is always 0, no matter what the base. That's the properties we just learned.
So since the base and the exponent are the same, it equals 1. And then for the second one, since it's raised to the power of 1, it's 0.
You're correct because the base and what the inside of the log matched. It was 1. This one is because we're taking the log of 1. We're going to draw the picture of the log function in a minute, but if we draw the picture, a graph of the log base 8, I'm just going to, it always goes through the point 1, 0. We're going to draw a picture. That's a picture of the log function. This is a vertical asymptote at x equals 0. The log of 1 is always 0. Why? Because if we rewrite this, log base 8 of 1 equals x. We rewrite it, we get 8 to the x equals 1. 8 to the x equals 1. Well, how are we going to, what power do we raise 8 to get 1?
8.
8 to the 8th power would be some huge number. 8 times 8 times 8 times. No, it's 0. Anything raised, remember, anything, it's okay. Anything raised to the 0 power equals 1. So that's why this is 0. I don't know if okay, did I answer your question?
Yeah.
Okay.
I was just confirming that's what was going on.
Okay, okay. I didn't think you said this exactly right. You said this one right. Okay. It was because we're taking the log of 1. The graph looks like this. It always goes through this point. And that's because of this. Okay. All right, so we have inverse properties of logarithms. I told you that exponents and logs are inverses. And if you remember from section 1.7, if two functions are inverses, that means f of g of x, if they're inverses, will always equal x, and g of f of x will always equal x. Inverses, if f and g are inverses. Okay, so inverses undo each other. It's like tying your shoes and untying your shoes. So logs and exponents. So here we have a log base b, and we have an exponent inside the log, and the exponent also has base b. So the bases match. They undo each other. It's like we're putting in x into the b of x function, and then we get b of x out, putting that into the log function. And we get back x. They undo each other. They're inverses. So x is no longer in an exponent here. We get x out. It's not up in the exponent. So also, if we take an exponent base b, this is b to the log base b of x. You have to, I need to make this a little bigger. This whole thing is up in the exponent. This is b to the log base b of x. So we're taking the exponent has base b, and the log has a base b. So they are inverses. They have to be the same base in order to be inverses. So log base 2 and 2 to the x would be inverse. Log base 2 of x and 2 to the x would be inverses, but not, you can't take log base 10 and be inverse with 2 to the x. You have to, the bases have to match. So if you're taking x and going into the log function, you get the log out, and then you go into the exponent, and you get x out because they're inverses.
Whoops. All right. Okay, so they're inverses undo each other. So you get x out. The next one, so examples of that are right here. So since the bases match, these are inverses, and so you get 6. The bases match, the 8 and the 8 match, so you're left with the inside of the log, but it's no longer inside a log, it's a 3. Okay? All right, and then we're going to do some graphing. So we have f of x equals 3 to the x, and g of x equals the log base 3 of x, in the same rectangular coordinate system. So we're going to graph it. I have these little tables down here. We pick convenient values of x, And then we put them in here. F of minus 2 is 3 to the minus 2. You have to remember about negative exponents. If you have x to the negative n, that means you can make a fraction out of it. To make it positive, you bring the base, which is x, to the other part of the fraction, and you make the exponent now positive. So these are a reminder of the rules of exponents. Just in time teaching, in case you forgot. Okay? So this is 1 over 3 squared, and it's 1/9, and that's approximately 0.1. And you can also use your calculator, but I think it helps to understand what's happening with these, what those rules mean, besides just blindly using your calculator. Okay, and so -1, you put in -1 for x, you get 3 to the -1 is 1/3, approximately 0.3. You put in 0, so 3 to the 0 is 1. And then you put in 1, 3 to the 1, it's going to be 3. So we have the points 1, 3, 0, 1, -1.3, and -2.1. Okay. Also, if you put in 2, you get 3 squared is 9. So we did that in section 3.1. We already graphed that. And now this is the inverse function. So if you're graphing an inverse function, these are inverses because it's log base 3 of x. The bases are the same, so those are inverses. So for inverses, you switch your x's and y's. So over here, we're going to get 0.1, -2. 0.3, -1. And 1, 0, 3, 1, and 9, 2. Okay, now we're going to graph those. So we have -2 and 0.1. -1, 0.3, 0, 1, 1, 3, 2, 9. And this is a horizontal asymptote. This is an HA at y equals 0. You label and mark your asymptote. Now, we're going to graph g of x. Now, we probably want to label this as f, or f of x equals 3 to the x. Or at least label it as f. Now we're going to graph this one, 0.1, -2. 0.3 is about -1. 1, 0, 3, 1, 9, 2. And this is a vertical asymptote at x equals 0. And then we do have, let's see if I have, do I have I can use a card. A straight edge. Y equals x. Inverses are symmetric about the line y equals x. So if this is the line y equals x. And those make sense. That's the easiest way to graph inverses graph these for these kind of equations. Okay, so this is the g of x. This is g of x equals log base 3 of x. Okay? Any questions? So you get it graphed. So we've got, those make sense? We had a horizontal asymptote here, now we have a vertical asymptote. Okay? You do have to write the x equals 0 and the y equals 0. You have to write the x equals and y equals. And asymptotes are not ordered pairs. You want to write them as they're equations of lines. Equations of horizontal lines are always y equals something. Equations of vertical lines are x equals something, a constant. So what's the domain of f? Our f function has a domain projected to the x-axis minus infinity to infinity. What's the range projected to the y-axis? It can never be 0, so it's 0 to infinity. You can also check out, find the domain and range from the graph, but we can also, the domain and range of inverses are switched, just like x and y's are switched. So the domain of f will be the range of f, and the range of f will be the domain of g. I mean, the domain of f will be the range of g. Okay? So they're switched. Just like inverses, you switch your x's and y's, you could switch your domain and range also. Does that make sense for the picture? Project this to the x-axis. The domain is 0 to infinity. It can't ever cross its horizontal, vertical asymptote. All right? And its range projected to the y-axis is going up at an angle very sharply, but still it's going up. It's minus infinity to infinity. Okay? Okay, so this is very typical of the graphs. So now we go to the next page, and we can generalize this. That example was where b was greater than 1. The base was more than 1. That's what it looks like. This is a general picture. This is f of x equals any base b to the x. This is y equals log base b of x. These are inverses. They have the same base. Here's the log function. Here's the exponential function when b is greater than 1. And if b is between 0 and 1, the base, say, is a half. It's going to look like this. The exponent goes the other way, and the log function is going like this. But this is more common. It's more common to have the base greater than 1. We use log base 10 a lot, and we use natural log, which is log base e, which is 2.7. So this is more common. All right, so in both these instances, we're talking about a log function, so we're talking about this function. And we're talking about this function. In both instances, there is the x-intercept is always at 1, 0. There is no y-intercept. The x-axis
is the vertical asymptote of the graph, and that is the y-axis, sorry. And that is the line x equals 0. Vertical asymptote is x equals 0. A log function is decreasing when the base is between 0 and 1. Remember, decreasing functions are falling the whole time. This is falling. A logarithmic function is increasing if the base is greater than 1. This is more common, but this is increasing its whole domain. From left to right, y is rising the whole time. Rising at different rates, but it's still rising. And the graph is smooth and continuous with no corners or gaps. So this is a generalization about the graphs. It's nice to understand these graphs. All right, so we're going to talk about the domain of a log function. Remember that the domain of an exponential function is all real numbers, and its range was a set of all positive numbers. And they're reversed, so that means the domain of a log function is all positive real numbers. And we could see that from the picture. The domain of just log x is 0 to infinity. But what if we have a function inside our log? Then we just need to make sure that function is greater than 0. So we can't take a log of a negative number or log of 0. You could try that on your calculator, and that's what this is saying. We have to make sure the inside of the log has to be greater than 0. The inside of the log must be greater than 0. Okay, so if you take your calculator, and here's this is log base 10 in your calculator. If you try to take the log of 0, your calculator's going to say domain, quit. Okay? And if you try to take the log of -1, it's going to say the same thing. It says non-real answer. It's not in the domain. We're not doing imaginary numbers in this, but you can take the log of 7. That's fine. That's a number. Okay. Okay. So now the next thing, let's find some domains. We know what the domain is when we have just x inside, but when we have something other than just x, we have to make sure the inside of the log is greater than 0. So you just set x minus 5 is greater than 0. The easiest way to solve that is to add the 5. When you add the same thing to both sides of an inequality, it doesn't flip the sign. When does the sign flip on an inequality? When you're what? Dividing by a negative, right? Or multiplying. So we only flip sign when dividing by or multiplying, let's write multiplying by a negative number. Okay? So we can add something to both sides. So we get x greater than 5. We want an interval notation. So that is, the domain is when that is x is
going from 5 to infinity. You could try putting in 5, you get 0. Can you take the log of 0? No. That's why we don't have a square bracket. Try putting in 6. Do you get a positive number in that log? Yes. Try putting in negative 4. I mean 4. Sorry. Okay, so that's the domain. I want to see this work on your test. Just 2 steps. 1, 2. Okay. To get full credit for the problem, you put those 2 steps in. All right? Because you can put this in your calculator and figure out the domain sometimes. And I don't mind you using your calculator to check, but in most cases I want you to do it by hand. All right? And then we need to make sure this inside of the log is greater than 0. So 2 minus x greater than 0. Okay, so we could either, I think it's a little easier to add x to make it positive. You could add x to both sides, it doesn't flip it. So you get 2 greater than x. Then you need to rewrite this with x on the left. So because the small end of the inequality was pointing toward the x, then you do flip the sign. Does that make sense? Do you guys get that? Or would you rather do it? So, I said you only flip the sign when you divide or multiply by negative. What I'm doing is I am rewriting this with x on the left. The small part of the inequality was pointing toward the x. I had to make the small part of the inequality point toward the x. So all I did was move the x to the left, because that's how we read it. We want to put x on the left, and then I had to put the small point pointing toward the x. Then you don't need to remember when to flip the sign if you do it this way. Or you could do 2 minus x greater than 0. You could subtract the 2, get negative x greater than negative 2, and then you divide by a negative 1, or multiply through by a negative 1, you get x and 2, and you have to flip the sign. I multiply through by negative 1. So I think it's easier to do it this way. What do you guys think? Whichever way you're used to doing it. Okay? And you can check by putting numbers in. Make sure you're not dividing by a negative, taking the log of a negative, or make sure your numbers work. And then we want to write that in interval notation. So that is going to be minus infinity to 2, and it's a parenthesis, not a square bracket. So people are still getting confused about those. Square bracket includes it, the endpoint. Let's see this. Okay, so that's domain. So we could do example, a real life example. We use logarithms for Richter scale, and we use logarithms for modeling heights of children. So here's a model that this models the adult height by a girl, and the girl has to be between 5 and 15 years old. So here's the equation. X is the girl's age, and f of x represents the percentage of her adult height. So, approximately what percent of her adult height has a girl attained at age 10? So they're telling you that x is 10. All you have to do is find f of 10. 62 plus 35 log of 10 minus 4. Okay, how many people think we should add before we multiply?
The parentheses first.
Yeah, we're going to do that. So we get 62 plus 35 log of 6. Okay, so how many think we're supposed to add these now? Good, you guys get it. We can't do that because of our Aunt Sally. Please excuse my dear Aunt Sally. She makes us multiply before we add. And so the 35 is multiplying, and so we don't combine this. This is not equal to, what was that, 97 log of 6. So, don't do that. Okay. So, 62 plus 35, and this is log base 10. If they don't list the base, this is base 10, and it's our log key on our calculator. LOG key on your calculator is log base 10 of X. Or whatever. So, we hit the log key, and it's 6. And it's because we have 10 fingers. 10 toes. I like to count by tens. All right, and the answer is 89.24. And remember, that's a percent, or 24. And so it's at age 10, she will have reached approximately 89% of her adult height. So, you can't see that. Let me get rid of the calculator. Okay. All right, and so this is called, just the LOG function, log base 10 is called a common log. So this is a common log. When you hear common log, that's log base 10. And that's the LOG function on your calculator. So this is base 10. Anytime we don't have the base written, it's base 10. And it's LOG. Now, we have another kind, and that we have natural logarithms with base E. And it's called the natural logarithmic function. Remember, E was the natural exponential function, or e to the x. So the function f of x log base E of x is called the natural logarithmic function, but it's usually expressed as ln of x. We don't write the base, it's base E, and it's an ln key. And I have no idea, I have to look it up. Why did they not do NL for natural log? Why did they switch it? Are we all, who knows, maybe NL was used for something else. There's probably a math history lesson there somewhere. Oh. Okay, but, so, and then if you're dealing with natural logs, the domain of, like the domain of all log functions, the domain of natural logs is the set of all positive real numbers. So the domain of natural log of a function will be where the function, or the inside of the log, is greater than 0. Okay, so we're going to do some examples of finding the domain again. So f of x equals natural log of 6 minus x. So we're going to take the inside of the log function, 6 minus x, and make sure that's greater than 0. So we can add x, 6 greater than x. We can write the x on the left, the small part has to point toward the x, the 6 goes on the right. So the domain is minus infinity to 6. Okay, what about this one? When we're going to square, we're squaring the number, and when we square a number, we always get a positive number or 0 if this equals 0. So when you square a number, gives you positive numbers or 0. So the only case you need to exclude here, because we're squaring, is you need to make sure the inside is not equal to 0. So if you add 5, you need to make sure x is not equal to 5. How do we write that in interval notation? We have the 5. We have these two intervals, minus infinity to 5, union with 5 to infinity. That's our domain. Check it. You can start putting numbers in there. If you put in 1, 1 minus 5 is negative 4. Square negative 4, you can get positive 16. You can take the log, natural log of 16. But if you put in 5 in there, 5 minus 5 is 0. 0 squared 0. Natural log of 0 is undefined, because that's the vertical asymptote. Okay, any questions? All right, does that make sense when you square? All right, so we got some more practice. This is a lot like that worksheet that's due next time. I mean, I was tempted to make it due in a couple days, but you know, it's a night class, and I don't want to do that. Some people work full time, so it's due not due till Wednesday. But I may grade yours early if you post them if you want me to grade it. All right, so this is, you got to follow the directions. Just write this in its equivalent exponential form. So if you want to write the 6 on this side, then you do the arrows. You start with the base, go across the equal sign to the exponent, and then that equals what was inside the log. This is its equivalent exponential form. All right, we want to write the 3 on this side, so we can do our nice arrows. We start with our base, go to the equal sign to the exponent, and then go inside the log. So b to the 3rd equals 27. That's the answer. We're just writing it. We're not solving an equation yet. All right, any questions? And now we're going to write in its log form. We're going to write log. We start by writing log. What's the base here?
5.
The 5, right? So we're going to write that down here. And the exponent is across the equal sign. So the exponent is 4. And that leaves 625 to go in the only spot left inside the log. Now we can check it. 5 to the 4 equals 625. Yes, you did it right. All right, on this one, you're going to have to rewrite this. This cube root of 64 can be rewritten as 64 to the 1/3. That's an exponent. The 1/3 up in the exponent. This is power over base. Seems like I told you guys this before. Power over base. So our first step was to rewrite the cube root of the cube root as to the power of 1/3. And that does equal 4. Now we're going to write log. What's the base? The 64. The exponent goes across the equal sign. And so the only spot we have left to put the 4 is right here. And you can check it by doing your arrows. 64 to the 1/3 equals 4. Yes, that's right. Okay, and then you can find the exact value of the logarithm without using a calculator. Well, when it says without using a calculator, that means that you need to show work. You could check it with your calculator, but you need to show your work that you did it without the calculator. So, you got log base 7 of 49. So you want to rewrite the 49 with a base of 7. Do you know what 7 squared is? If you don't, you could start just typing in your calculator 7 times 7 or 7 squared. So to evaluate without your calculator, you're going to end up with bases matching. So you have log base 7 of 7 squared. These are inverses because the bases match. And so the answer is 2. They undo each other and you're left with the 2, but it's not an exponent anymore. So that's the work. One step. I just want you to show one step here. All right. Log base 6. Now, how do you write 1/6 as an exponent? Do you remember that negative exponents that you can write 1/6 as 6 to the negative 1? So, remember, x to a negative exponent is 1 over x to a positive exponent. So you can go the other way too. 1/6 can be written as 6 to the negative 1. And now that you have the bases matching, you can write that. They undo each other. You've got an answer of negative 1. Okay? Alright, this was a little harder. But how can you rewrite 9 so it has 81 as a base? Well, the square root of 81 is 9, right? So 81 to the 1/2 will be 9. So you can rewrite this as 81 to the 1/2. Now your bases match and you get 1/2. If you have trouble coming up with that, you could do that a different way. We'll go ahead, I'll show you a different way to do that. Is you write log of 81, log base 81 of 9 equals x. We're trying to figure out what x is. So we rewrite that as an exponent, 81 to the x equals 9. So 9 squared to the x equals 9 to the 1. So 9 squared to the x power is 9 to the 2x. We multiply. That's the power to power rule. Equals 9 to the 1. That means 2x equals 1. So x is a half. And this is one way to solve a logarithmic equation. This is section 3.4 actually. But if we get the bases to match, we can set the exponents equal. If we have a single exponent on both sides of the equal sign and the bases match, we can set the exponents equal. We can also do the opposite. We can raise both sides of an equation to the same base. But, so x is a half. So we set this to x, so this equals a half from that way. I don't know which way makes more sense. But if you can't think of how could you rewrite 9 so its base is 81, then you could do it that way, the equation. All right. Any questions? All right. What's the answer down here? Any time you take the log of 1, our log function is going through the point 1, 0. So when x is 1, y is always 0 no matter what the base. The log of 1 is always 0. Okay? And here the bases are matching, so they undo each other, so we get a 6. Here the bases are matching, so they undo each other, we're left with 23. And the last page. Okay, so we've got more. We're going to find the domain of the function. So more examples of finding domain. This is log base 10. Of 7 minus x. Anytime you see log by itself, that means log base 10. But finding domain, we don't care what the base is. Doesn't matter. All logs, you have to make sure the inside of the log to find domain is greater than 0. So we can add x, 7 greater than x, then x is less than 7. So the domain is minus infinity to 7. Okay? Here we're squaring, so we just need to make sure that x minus 7 is not 0. So x can't be 7, so that is minus infinity to 7, union with 7 to infinity. All right, in the last examples, this is an understood log function is base 10. So the bases match, they undo each other, so you 3. You're left with what was inside the log. E to the natural log of 300 has base e. These undo each other. They have base, the exponent has base e, the log has base e. They're inverses. This is going to equal 300. this is all inside the log here. We have e to the natural log base e of 7x squared. So the bases match, they undo each other, and you're left with 7x squared. Okay. All right, so that's section 3(2). Any questions? You need a break now, and then we'll start 3(3). Yes, I can take it longer. All right, we'll take a 5-minute break.